Hello everyone and welcome to this video. Today I will provide a review for your first midterm exam. Your first exam will only cover chapter 3 of your textbook. In this chapter we talked about horizontal and vertical alignment and pretty much everything that I covered in my notes are going to be on the exam. As you know, the book has more materials, but anything that is not covered in the class will not show up on your exam. You can see the date and time of your exam on this slide. I want you to keep in mind that the exam is given to you on Moodle. The exam will start exactly at the given time, at the start time of the class, and you will have 90 minutes to do your work. The exam, if it's done in class, does not require 90 minutes. It will require something in the order of 60 to 70 minutes. What I have done here is that I have given you 20 to 30 minute extra time so that you can take the photo of your work, as I will be explaining in the next slide, and upload it to Moodle, because you need to show your solution approach to each of the questions that you see on the exam. The exam will have 3 questions. So our exam will be on Moodle. I'm giving you calculated questions. So the input to the question from one person to the next is changed. You need to do your calculation. You will need to use several equations, and based on the input that you have on the question, you will find your answer. What is critical here is that you need to write your solution approach neatly on several papers, and at the end of the exam you need to either scan them or take high quality photo of them and post them on Moodle. Not only you enter your final exams on the Moodle website, but also you need to put a circle or a box around them on your question sheets. So if you put the right answer but there is no solution approach, I'm afraid that you're not going to get credit for that answer. So it's very critical for you to show your solution approach. And also that is important because if your final answer is wrong, I want to be able to go back to your solution approach and give you some partial credit. Okay, so make sure that your approach, your solution approach, is there. You can use any calculator that you want. There is no restriction on the calculator, but of course in this exam you cannot communicate with each other or with others about any questions. You cannot go to websites that post answers to questions such as Chegg and put the questions there and get answers. So that is considered as cheating on this exam. The exam is closed book and closed notes, but you need to prepare a cheat sheet, a letter-sized cheat sheet, and you can write or type on both sides of that cheat sheet, and you can bring it or use it during your exam. What is important here is that you are not allowed to write exact solution to any question on that cheat sheet. And at the end of the exam, what you need to do is to take a photo of this cheat sheet and also upload it on the exam. Now, when you want to prepare for this exam, the best way to do so is to start with going through the lecture notes, the videos that I have posted for you. Go through the examples that I have done in the class, then go over your homework assignments and try to redo them. Then go to your book, and if there are examples on the book that we haven't done in the exam but they are related to what we have covered, go through those. And if you have done this, you're not going to have any issue on the exam. It is important for you to start right away and don't let things to pile up. This is going to be a very easy exam for you if you start now, but if you start the night of the exam, it's going to be very hard to be able to pull everything together and do a good job on the exam. So I want to make sure that you start preparing right away. If you need any table for any of the questions, those are going to be given to you. So you don't need to bring tables with yourselves to the exam. But if there is any equation that you need to have those on your cheat sheet. I am not providing equations for the exam. So one purpose of that cheat sheet for you is to have all of your equations there. And also when you try to create that cheat sheet, it gives you a good opportunity to go through all lecture materials one more time and pretty much summarize everything that is given to you there. Now, for the rest of this video, I want to go through several examples. You have seen those previously in our lecture videos. The reason that I have put them here is to facilitate accessing them for you a little bit better, and also these are the examples that are going to be similar to what you're going to be seeing on the exam. Let's go through them. So here is an example that I would like everyone to try to solve. I'm going to go through the example and then I would ask everyone to pause the video for a few minutes, grab a piece of paper and try to solve the example on your own without looking at the answer. And then we will go through the answer together. So what we have is that we have a 600 feet equal tangent sag vertical curve. The length is 600 feet. And this curve has a PVC that is stationed at 170 plus 0, and its elevation is 1,000 feet. G1 is equal to negative 3.5. G2 is equal to 0.5%. Determine the stationing and elevation of the PVI, PVT, and the lowest point on the curve. So what I would like to ask everyone here is to pause the video and try to solve this problem on your own and then continue with the video. So I want to first find where is the PVI or where the PVI is. So PVI is the point of vertical intersection. We have an equal tangent curve, so we know that PVI is L over 2 feet to the right of the PVC. We have the station of PVC. We know L is 600 feet. So what we just need to do is to add the station of PVC in feet to 300 feet. So the station is 170 plus 0. If we convert that to feet, we just multiply that by 100. So 170 multiplied by 100 would be 17,000. We add 300 to that. So the station would be at 170 plus 0. Now we want to find the station of PVT. We know that PVT is again L over 2 feet to the right of PVI. So you can either add 300 feet to the station of PVI, or we know that PVT is L feet after the PVC. So that's another way to find it. So that's what we have done here. PVT is equal to PVC station plus 600 feet. Again, 17,000 plus 600, which is going to be equal to 176 plus 00 stations. So we want to find the elevation of PVI and PVT, and we have the elevation of PVC, and we have the slope of the first grade, it's negative 3.5. So that means that the elevation decreases by 3.5 feet per station, and from PVC to PVI we have 3 stations. So if you want to find the elevation at PVI, you need to take the elevation at PVC, or 1000, and subtract the amount that the elevation will be decreased, which is going to be equal to 3.5 per station multiplied by 3 stations. So if you just find this number, that will give you 989.5 feet. And we know that from PVI to PVT, the slope is 0.5 or 0.5 feet per station. That means that per station, the elevation is going to be increased by 0.5 feet. So I have the elevation as at PVT, it is 989.5. I know how many stations I have between PVI and PVT, that's going to be 3 stations. And I multiply that by 0.5. So the elevation at PVT would be 991.0 feet. The question also asks us about finding the location of the lowest point on the curve, and that means what is the x and y of the lowest point on the curve. And I would like for you guys to think about one important characteristics of this point. So we have a curve that looks like this, and its lowest point has a special feature. What is the special feature of this point? Well, if we were in the class, I would say I will give a bonus point to anyone who answers this point, but unfortunately we are not. So the special feature of this point is that its slope is 0. As a result, if we want to find the location of this point, we can take the first derivative and set it equal to 0 and find the x of this point. So if we take the first derivative of ax squared plus bx plus c, what we'll have is 2ax plus b, and we will set this equal to 0. We already know that b is equal to g1. G1 is equal to negative 3.5. A is equal to G2 minus G1 over 2L. And keep in mind that G1 and G2 are in percent and L is in station. So G2 is equal to 0.5 negative minus negative 3.5 over 2 times 6. That gives a value of 0.333 for A. Now, if you put these values in 2ax plus b equal to 0 equation, what you would have is this equation that you can see on the board or on your screen. So 2 multiplied by 0.333 multiplied by x plus negative 3.5 is equal to 0. If you solve that, it's going to give you x equal to 5.25 stations. What I would like for everyone to keep in mind is that x is in stations, G1 and G2 are in percent, L is in station, and y is in feet. So if you have x, you can put it in the equation for the parabolic curve, and you can find the elevation of the lowest point. Y equal to ax squared plus bx plus c. C is equal to 1,000. B is equal to negative 3.5. And A is equal to 3.333. So if you just put these values in your calculator, you will get a value of 990.81 feet for the elevation of the lowest point. X is equal to 5.25 stations and Y is equal to 990.81 feet. So I think this is a very good point to go through an example. And again, like all previous examples, I'm gonna go through the question, then you're gonna stop or pause the videos for 5 minutes. You're gonna do it on your own, and then we are gonna go through the solution. So we have a highway that is designed up to AASHTO's guidelines. The design speed is 70 miles per hour. And at one station, we have an equal tangent vertical curve that connects grades of +1 to -2. So this is a crest vertical curve. First you go up the hill, then you go down the hill. So we want to determine the minimum length of curve according to AASHTO standards to meet stopping sight distance requirement. So please pause the video at this point for 5 minutes and go through the example and then continue. So what we will be doing here is that again we're going to assume that the grade is 0 or the slope is 0. So the design speed was 70 miles per hour. If you go to table 3.1, you will see that the required stopping distance is 730 feet. So that's the distance that you need as a driver to react and also to stop the car. Now, if you remember the equations that we saw, they have two parts. One says L is more than stopping sight distance. The other part says L is less than stopping sight distance. So we have the stopping sight distance, but we don't know the lengths. We want to find out what is the minimum design length, and then we are gonna either go with that or a little bit longer than that, but we don't know if that's going to be less or more than stopping sight distance. So as an engineer, you need to assume, to make an assumption here. Let's assume that L is more than stopping sight distance. Find the value of L and then we check if it is more or less than the stopping sight distance. If it's more, we are good. If it's less, we need to do something. So let's start. I'm going to assume that L is more than the stopping sight distance. So I'm going to be using the equation that is given for that condition, which is Lm equal to A in stopping sight distance square over 2158. So my G2 is -2, G1 is 1, so A would be equal to -2 minus G1, which is +1, which is equal to 3. And that would be 3%. So that's what I have here. We also found stopping sight distance to be equal to 730 from table 3.1. So you can see that I'm multiplying 3 by 730 square and divided by 2158. That gives me a value of 740.82 feet. So that's the minimum length that I need on that curve. You can see that this length 740 is more than 730 feet. So that means that the assumption that I made at the beginning is satisfied. So I'm good. So the length of the vertical curve should be at least equal to 740.82 feet. So here we have the next example, and I think it's a good place to pause for this class, and we are going to start going through this example in the next video. Hello everyone. Today I would like to continue by going through example 3.8. Just a quick reminder is that we are working on designing or finding out what has to be the minimum length of a sag vertical curve so that we can accommodate enough side distance. Now this example actually is a very good and comprehensive example, and pretty much it will recap a lot of things that we have learned so far about sag vertical curves and in general about vertical curves. So here is the example. We have an equal tangent sag vertical curve. It has an initial grade of negative 2.5. It is known that the final grade is positive. So we know that it's positive, but we don't know exactly what the value of the slope is. We also know that the low point is at elevation 270. So the low point is at elevation 270 and station 141. The PVT, point of vertical tangency, is at elevation 274 and the design speed of the curve is 35 miles per hour. Determine the station and elevation of PVC and PVI. So before looking at the solutions, I would like for you guys to pause this video for 7 or 8 minutes, go through the example, try to do it on your own, and then continue watching the video. So before going to the solution, I want to tell you this one more time, that whenever you are working on problems like this, if you start drawing them, all of a sudden the problem becomes way less complex. I'm not going to draw it here in this video, but I want you to always consider it, no matter if that's a class problem, if that's an example problem or homework problem, or in your exam, you definitely want to try drawing it. When you draw it, you look into the curves, the tangents, you look into the triangles that are there. All of a sudden, a lot of things make sense. It becomes a lot easier. So first thing that we want to do here is to find the K value, the design K value for this problem. So if you remember, table 3.3 gives us K values for different design speeds. So if you go to that table, you will find out that for the design speed of 35 miles per hour, the value of K is 49. So what we did was that we selected design speed of 35. We went to table 3.3 and we found the value of 49 for K. Now, if you go back to probably the first or the second class that we had, you would remember that I introduced a hard way to find the location of the low or high point. You had to go through taking first derivative of the formulation of the parabola and going through a lot of calculations to find the location of the high or low point. Or there was an easy way that you could use K value, the initial slope of the tangent, and by multiplying those two, you could have found the location of the high or low point. So this is a sag vertical curve. So when we are talking about the location of high point or low point, we are really talking about the low point. So if you multiply k, which is 49, by 2.5, which is the initial slope, you would get a value of 122.5. So that means that the distance of the low point from PVC is 122.5 feet, or in stations it is 1 station and 22.5 feet. So if you just subtract this value from the station that is given for the low point, we can find the station of PVC. The given station for low point was 141. This was given in the problem. So we subtract 1 station and 22.5 feet. It gives you a station of 139 plus 77.5 feet for PVC. We have the elevation of the low point. It is 270 feet. We know that x is 12.20, it's 122.5. So these are known parameters to us. Also, we know that the b parameter of the parabola, if you remember, the parabola is y equal to ax squared plus bx plus c. B was one of the parameters of the parabola that is equal to g1, or negative 2.5. So we want to go forward from this point and find other parameters of the parabola. Okay, we have determined the value of b. It is equal to g1, and now we want to find the value of a. If you remember, a is equal to g2 minus g1 over 2l. Now here it's a little bit tricky because we don't have the value of l, but we know that g2 minus g1 is equal to a, and at the same time, if you remember, k was equal to l over a. As a result, L is equal to K multiplied by A. So I'm gonna substitute L in the denominator here with K in A. So I'm gonna have G2 minus G1, or A, divided by 2L, which is 2 over 2 into KA. And what that 100 does here, what it does is that it's gonna fix the the units that we are using here. So if you have this, you see that you can cancel out a with a. 100 goes up, and then we are gonna have 2 into k, which is 2 over 49, 2 into 49. So you have 100 over 98, or 1.02. That's the parameter that we need to find in our parabola's equation. So we have y equal to ax squared plus bx plus c. Now the only thing that is left is finding c, and we know that at low point the elevation is given. So if I just insert y of low point, which is 270 here, and I have a 1.02, I have b, which is negative 0.25, and for x, if I put the x of low point, it's going to be 1.225. So if you just put all of these in this equation, you find out that the only unknown is c. So you just have a very simple equation to find c. C is going to be 271.53 feet. That's going to be our elevation at PVC. Now we have all the parameters here. We have a, B, C. So pretty much this parabolic equation is all known. So what we need to do here is to go and find the lengths of the curve. And to do so, now we know that the elevation at PVT is 274. So if A is known, if B is known, if C is known, if I know that the elevation at PVT is 274, if I put L or if I find X, that's gonna be the length of the curve because from the origin to PVT, X is equal to L. You move on the horizontal plane L feet or L stations, depending on how you have defined everything. So that's what I'm doing here. So 274 is equal to 1.02 L squared plus negative 2.5 L plus 271.53. So what you need to do is to solve this quadratic equation. It's going to give you two solutions. One is going to be not right and negative. The other one is the one that you see here, 3.2. And you see that because we have put everything in stations or in feet per station for the slope. The value of L is in station. So it's 3 plus 2 or 6 stations or 320 feet. So now you can find the station of PVI that's equal to station of PVC plus half of L. So that's just simple calculations. I have 139 plus 77.5. I add the half of the length of the curve to that. So the station of PVI is going to be 141 plus 37.8. The elevation of PVI, you just need to know the elevation of PVC and add G into L over 2 to it. Now you can see that here I put G in feet per feet, then I had to put L in feet, so that's going to be 271.53 minus 0.025 in L. That's going to be 267.52 feet. That's the elevation of PVI. Or what I could have done was to write it this way, 271.53 minus 2.5, and then if this is 2.5, it means that it is feet in stations. So now I need to write the lengths in stations. That would be 3.264 over 2, which is going to give me exact identical solution. So in this example, we have a horizontal curve on a 4-lane highway. And one thing that you want to keep in mind, whenever we say 4-lane highway, 6-lane highway, we are talking about the total number of lanes. So 4-lane highway means that I have 2 lanes in each direction. In this 4-lane highway, my super elevation is 6%. Central angle is 40 degrees. The road has 10 feet lanes and 8 feet shoulders on both sides with retaining walls right at the shoulder. So it means that at the shoulder, so we have something like this. So we have 2 lanes going this way, 2 lanes going this way, and then we have the shoulder, and then at the shoulder we have a retaining wall. So what that means is that everything past the shoulder is obstructed and you cannot see. So this is 8 feet, this is 10, 10, 10, and 10. Okay? So the PT is at station 322 and PI at station 320 plus 08. So one thing to keep in mind is that when we talk about PT and PI and everything, we are talking about the center line of the curve, which is here. Okay? So PT, when the curve ends, is at 322 plus 50. PI is at 320 plus 08. And the question is asking for the highest safe speed, and it wants you to round it to the nearest 5 miles per hour. So I have already drawn this for you, but I would like for you to pause the video here, go through these, and this is one of the longer examples, so probably it's going to take you 10 to 15 minutes to do this example. And when you're done, come back to the video and watch how we go through the details of this example. Okay, so let's take a look at the solution, and I have put some key input on the top of the slide so that we don't forget them. So we want to start with finding the station of PC. And the reason that I want to do that, and here I'm focusing only on the center line of the curve, is that we had a piece of information. We know that PT is at 322 plus 50, and we know that PI is at 320 plus 08. And we know that we can find the station of PC by either subtracting T, this is T, from the station of PI, or by subtracting L, which is this length, from the station of PT. So both of these are going to take me to the station of PC. So what I can say actually is that I can say what I can say is that station of PI minus T is equal to station of PT minus L. So if I do that, then I can start calculating some of the unknowns that I have here. So I can say the station of PI, and I'm writing it now in feet, minus T is equal to station of PT minus L. For T, I'm going to replace it with R into tangent of delta over 2. For L, I'm going to substitute that with pi over 180 into R into delta. So I have delta. Delta is given to me. So the only unknown here is R. And remember, R is to the center line of the curve. So I can determine R by replacing the value of delta into the equation. I'm going to have 724.2. What is R sub V? So let me draw the curve one more time. So this is the center line. I have 2 lanes on the top. I have 2 lanes at the bottom. So this is R. I want to know, this is R. I want to know RV. So RV here is going to be equal to R minus this width minus half of this width. This width is 10. This one is going to be 5. And that's what I have done here. So my R sub V would be 709.2008 feet. So we could successfully find R and R sub V. And now we want to continue to find what is the maximum speed that a vehicle can go through and be safe on this horizontal curve. And there are really two main things that we need to consider. And I want you to think about it. So if you are driving on a horizontal curve, what are the things that are going to influence your speed? The first thing that comes to my mind is my vehicle's cornering capability. So do I have enough radius and enough super elevation and enough friction that my vehicle is not going to drive off the curve? Okay, that's the first thing. The second thing is that do I see enough on the curve that I can stop safely? So let's say that you have a curve that if you go 50 miles per hour on that curve, you're not going to drive off the curve. But in order to be able to stop safely, you need to be going at most 35 miles per hour. So what is going to be the speed that you're going to use on that curve? It's not going to be 50. It's not going to be 45 or 40. It's going to be 35. Because if you go more than 35, you're not going to have enough time to stop your vehicle if you see something that's stopped on the curve. Now let's take a look. Think about the opposite condition. What if you can go at most 50 miles per hour on that curve and you're not going to drive off the curve at 50, but if you go up to 70 miles per hour, you can still safely stop your car if there is something on the road. So what is going to be the highest speed that you're going to travel on that road? It's going to be 50, right? Not 70, because if you go more than 50, you're going to go off the road, right? So now in the next couple of slides, I want to do that. I want to find what is the maximum safe speed that I can go on the road and don't drive off the road, and also what is the maximum speed that I can be traveling there, and if I want to stop my car, I have enough time and distance to stop it before I hit something, an object that is on the road. So I'm going to start with vehicle cornering capabilities. So we find the length of the road. So that is going to be just putting everything into this equation. L is going to be equal to pi over 180 divided by R into delta. So the length is going to be 505 plus 505.588. Station of PC is going to be equal to station of PT minus L. So if you just do that, you get this station for PC. And now we are going to check for vehicle cornering requirements. And we go to table 3.1, and we know that the super elevation is 6%. That was given to us. Okay? So if you have a super elevation of 6%, if the design speed is 50 miles per hour from the table, our R sub V is gonna be 833. So if you are going at 50 miles per hour, you need a radius of 833. What we have is 709. So that is not adequate. We cannot go at 50 miles per hour. Let's try 45. If you go at 45 miles per hour, the R sub V that is required is 643 feet. How much do we have? We have 709. So that is adequate. So from vehicle cornering capabilities, we can go at most up to 45 miles per hour. And remember, these numbers are coming from table 3.1. So let's save 45 miles per hour in our memory. Now we are gonna work with the stopping side distance. So how much clearance do we have? The shoulder width is 8 and the lane width is 10. So this is my shoulder, that is 8. This is my lane width, that is 10, and we are talking about the center line of the critical lane. So this is another 5. So my M sub S is equal to 8 plus 5, right? Or 13 feet. That is the amount of clearance that I have. So let's go to table 3.1 again and find the required stopping side distance for a speed of 45. Why do I start from 45? Because 45 was the highest speed that I could go from vehicle cornering capabilities perspective. So if I go with the speed of 45, my stopping side distance is gonna be 360. I'm gonna put it in this equation, and that is gonna give me the required M sub S. So the required M sub S is equal to 22.72. How much clearance do I have? 13. How much do I need? 22. So the need is more than what I have. So 45 is not gonna work. What do I do next? I'm gonna reduce the speed by 5 miles per hour. And that would give me a speed of 40. So if my speed is 40, the stopping side distance that I get from that is 305. So if I put my R sub V, which is 709, here, and stopping side distance of 305, I get a required M sub S of 16.33. My required side clearance is 16.33. I have 13 feet. So this is not gonna work either. I'm gonna reduce the speed to 35 now, another 5 miles per hour reduction. So with that, my stopping side distance from the table, and again, same table 3.1, is gonna be 250 feet. I'm gonna put everything in the equation, and I'm gonna get a required side clearance of 10.99 feet. So this is less than 13. It means that 35 miles per hour works. If you remember, from vehicle cornering capabilities, we found 45. Here we found 35. So the lowest of the two is going to govern what we can do and what is the fastest speed that we can go there. All right, I hope that this review session was helpful for you, and if you have any questions, let me know. I will be holding an office hour this week, and you will be receiving an email with details soon from me. Best of luck.